Our next simulation example will be the solvation free energy of methane. Normally, when you have a single liquid and add a second liquid to it, when the two liquids mix completely, that means each molecule is surrounded by not only its own neighbors, but also neighbors of a different kind. So, if all possibilities are allowed, then mixing is possible. But suppose A and B are not interacting with each other strongly, say for example, oil and water. Oil and water will not mix because there is a lot of repulsion between the two objects. So, before we want to know whether something is miscible or not, one idea would be to take a single molecule and see what is the free energy of solvating that molecule in a liquid. That is what we call as free energy of solvation, and in this particular lecture we will see how to solvate a molecule in a liquid. So, the first slide tells you that there is a one molecule there and you try to solvate it, and if the free energy is positive, that means it is not a favorable arrangement. So, to find out how that delta G comes about, this whole lecture is about. So, can we have the next slide? Yep. So, in this slide we will see how to hydrate a particular molecule. Go to the next few. Okay. So, this is called a thermodynamic integration method. What we do in this is insert a cavity in a liquid, and that cavity is initially not interacting with the medium. So, and in that cavity you put a molecule. So, when lambda equal to 0, that cavity does not interact with the rest of the medium. Now, slowly when lambda goes from 0 to 1, the interaction is completely established. See, for example, suppose I have which is this molecule we are considering, methane?
Methane, yeah.
So, suppose I have a methane molecule, we know that there are 5 sites in it, 1 carbon and 4 hydrogens. So, when they do not interact with the solvent, that lambda is 0, and if I suddenly put lambda equal to 1, there will be lot of repulsion and the system will not like it very much. Therefore, what we do, say lambda equal to 0, no interaction. When lambda is a small value, here we have shown 0.04, but I will actually put 0.01 or 0.1. When I put lambda equal to 0.1, the entire interaction is not turned on. Only if it is 0.01, only 1% of the interaction is turned on, and when 1% of the interaction is turned on, this 1% interacts with the rest of the solvent and slowly aligns that solvent in a favorable arrangement. So, next time I make lambda equal to 0.02. So, that is I enhance it a little more, then more and more interaction will occur, and eventually in the end lambda equal to 1. So, my entire interaction is put on, then that is my final simulation. To find out the free energy from 0 to 1, first I have to take, at each step there is an interaction. So, my Hamiltonian now, or the interaction, it depends on this parameter lambda. So, I take a derivative of h with respect to lambda, that is called dh lambda by d lambda. I take an ensemble average. What is the meaning of ensemble average? I am going to do a large number of steps in my simulation, say 100,000 or 1 million steps. So, when I average that quantity, I am getting dh lambda by d lambda at each point in the simulation. So, once I have that for several lambda points, let us say 100 lambda points, I start with 0.01, 0.02, 0.03 and so on, and when I integrate all from 0 to 1, that entire integral gives me the free energy of state B minus free energy of state A, that is called GB minus GA, that is your delta G, that is the free energy of solvation. This is what we want to calculate using the GOMACS software. So, all the steps needed will now be introduced to you. You can start with the next step. So, you see even in the picture, initially there is nothing, lambda equal to 0, lambda equal to 0.4, it is a light white ball, then it becomes more colored, and eventually when lambda equal to 1, the entire interaction is switched on. So, this is a switching off, switching on procedure, and we will see how GOMACS enables you to do this.
So, first we have to prepare the simulation box, right. We want to calculate the free energy of hydration of methane. So, the input file that is required is methane.pdb. Now, we have the pdb file of methane. Now, what we do, we create a box around the solute molecule, and to prepare the box we will use the command edit conf. So, edit conf minus f methane.pdb minus o box.gro, that is my output file, gro is the Gromov structure file, and minus bt dodecahedron, bt is the box type, dodecahedron is my box shape, and minus D1. So what will it do? It will create a dodecahedron box with the minimum distance between the solute and the box edge being 1 nanometer. So after we have prepared the simulation box, now what we have to do? We have to solvate the solute molecule. Now to solvate the solute molecule, we will use the command genbox as we have used in case of S-peptide. So we will type the command genbox space minus cp box.gro space minus cs space minus o solvated.gro space minus p topol.top.
Why do you have two of these next to each other, minus CS and minus O?
Minus CS is used for the solvent input, and minus CS solvent input, when you download GROMACS,
Okay.
there is already spc.gro downloaded automatically. So it will take the spc.gro file
Okay.
from GROMACS, and minus CP is for the solute size.
Okay.
So it will add the solvent from spc.gro, and then it will create my output file, that is solvated.gro, and it will also modify my topology file. Initially in my topology file, I will only have the coordinates of methane, the force field parameter of methane molecule, but now since I also have water molecules, so it will add water molecule in my topology file. As we have already seen that in case of S-peptide also, it modifies the topology file, right?
Okay.
So it will solvate my methane molecule and it will create a new topology file. So we can view the topology file by using the command vi, that is vi topol.top, and now we will perform energy minimization. So what we have solvate.gro, which is methane solvated by water, then we have topol.top, and we have em.mdp. em.mdp is my energy minimization molecular dynamics parameter file.
What about the sizes of the boxes? Where will, now in this case you have a dodecahedron.
Yeah.
What size will it choose, or we have to specify that in some file?
You can either specify it, or it basically what it does, it will take, I have specified my distance between the solute and the box edge,
Okay.
that is 1 nanometer. So it will
Okay.
create a box around it.
Okay.
So when you type the command edit conf, it will display on the screen what is the box length that it have chosen, right?
Okay.
Now when it will solvate it, it will slightly modify the box length.
Okay.
So it will also be displayed in the screen. You can open the file solvate.gro by using the command vi,
Okay.
and then you go to the last line, it will display you the box length.
Okay.
What is the box length, and it will, the box length will be according to the type of box that you have chosen. Suppose in this case I have taken a dodecahedron box, so it will give me the box length according to a dodecahedron box.
Okay.
If
But
I
it can be done using a cubic box
yeah,
also.
it can be done using a cubic box. So what you do there is minus bt, then instead of dodecahedron you type cubic.
Okay.
So it will create a cubic box.
Okay.
So now we have
So the
solvate.
advantage of a dodecahedron is that there are less edges.
Yeah.
See, in a cube the edges are very sharp. So when you have a dodecahedron, there are less sharp edges and the periodic boundaries are not as strong, because a cubic is a very strong periodicity,
Yeah.
whereas a dodecahedron it's much smoother. Ideally spherical boxes will be nice, but a sphere cannot be completely surrounded by all the sphere, there will be gaps.
Yeah.
So you need only those edges where infinite medium can be created by replication. Okay. Yeah, go ahead.
So now we already have solvate.gro file, which is my methane solvated by water. We have the topology file and we have energy minimization file. This em.mdp file is same for all the case, like we have done in argon, water methanol,
Mixture,
yeah,
S-peptide.
S-peptide. The format doesn't change.
So EM is the final energy minimized configuration.
No, this is the
Input.
molecular dynamics parameter file.
Okay.
This parameter file, it remains almost the same. The
Correct.
only thing we can change here is the cutoff length.
Okay.
That will be according to my box length.
Okay.
Right. So now to perform energy minimization, we will first need a TPR file. So to generate a TPR file, we will use the command grompp space minus f space em.mdp, which is my energy minimized molecular dynamics parameter file. Then minus c space solvate.gro, which is the Gromo structure file, and minus space p space topol.top, that is a topology file, and then minus space o em.tpr, that is my output file. So now we'll use the TPR file to generate all my energy minimize configuration. So what we do, we'll use the command mdrun. So mdrun space minus v space minus DEFFNM space EM. So I'll get my energy minimize configuration, that is em.gro, and it will also write the minimum the minimum value of potential energy. So after this, what we do, we proceed towards the equilibration. So it depends which type of simulation you want to do, whether you want to do in NVT or you want to do it NPT.
Where is this specified?
This is specified in the equal.mdp file.
Okay.
Right. So for equilibration, again we'll need the GRO file from energy minimization. We will need the topology file and the MDP file for equilibration. So here, how do you specify? Suppose I want to perform an NPT ensemble. So what is that required? We need to keep the pressure constant, temperature constant, and number of molecules constant. So number of molecules constant is being taken care of by the periodic boundary condition that we are using. For pressure being to keep constant, we will use the a barostat to keep the pressure constant, and to keep a temperature constant we will use a thermostat in the MDP file.
Since there are many ways of keeping pressure constant and temperature constant, does the GROMACS give you different options for them?
Yeah, it does give different options for them. You have to choose accordingly that what is the kind of barostat or thermostat that you want to choose.
Are there options like 1, 2, 3, or you have to give the name of the
You have to write the name.
Okay.
You have to write the correct name of the thermostat or barostat that you want to use.
Okay.
So once you have the MDP file, em.gro and topology file, we'll again generate a TPR file here. So the command we'll use is grompp space minus f space equal.mdp, where it is the molecular dynamics parameter file for my equilibration in NPT ensemble, then minus c space em.gro, that is my energy minimize configuration, then space minus p topol.top, the topology file, then space minus o, it will be equal.tpr. So after I get my equal.tpr file, I'll run mdrun using the command mdrun space minus v space minus DEFFNM equal.
So it will create all files with the starting name equal.
Yeah.
Okay. How many will be? Which are the files?
I'll need the GRO file for my next step.
Okay.
Right. So after it is done, so as you have already said earlier that we need to create a lambda point here. Lambda, it specifies the path between A and B state. So for our sake, we will create lambda point, say first point will be 0, right? Then we will have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6 till 1.
Correct.
So and we
0.01, 02, 03?
Yeah, that depends on the user that how many steps
so
he or she wants to take between these two.
Yeah. So you are not showing all the 100 directories, you have shown only 6 or 7 of them.
Yeah.
Okay.
And now we have to populate all these lambda directories. What we need is, we need the GRO file from the equilibration, we need the topology file, and we need the run.mdp file. Now this MDP file is different from the equal.mdp or em.mdp file, right?
So do you have to load all the directories with the 3 files?
Yeah. We have to populate it because these 3 files need to be there in each lambda directory.
But suppose I want to do lambda 06 calculation, for that will I not need the configuration from lambda 05?
No, you have the equilibrated configuration, right?
Right. Okay.
So once you have the equilibrated configuration, you can start your calculation at each lambda point separately. You don't need a file from lambda 05 for 06.
Okay.
So this is the run.mdp file. What we do here, we use your stochastic dynamics. So in integrator we have to write SD, which specifies stochastic dynamics.
So which is this file? You are showing the MDP file.
Run.mdp file.
Okay.
And then we also have to specify free energy parameters.
Okay.
Right, here it is shown the free energy parameters, where free energy which is equal to yes, that means yes, you are calculating free energy.
Okay.
Then couple molecule type, here you have to type the residue name of your solute,
Okay.
which you want to couple.
Okay.
Then you will have the init lambda, that is the initial
Initial
value
value
of
is 0.
lambda.
Okay.
So initial value is 0, right? Then you will have soft core potential, that is sigma value.
Correct.
Then power and all this free energy stuff.
Okay.
Like you want to couple intramolecular interaction, then there will be lambda, then there will be foreign lambda, that is the rest of the lambda values. So
Okay.
these are the free energy parameters that you have to specify in your MDP file. If you go in the GROMACS site,
Okay.
it gives you a list of parameters that you can keep for your free energy calculations. So it is already available there. It's written in detail that what are the parameters that you will need for an MDP file. You just have to add all this line in at the end of your MDP file that you
Okay.
are already using for your previous calculations.
Have they given some examples in the?
Yeah, there are examples
Okay.
given in there.
So methane is one example, or we are creating separately?
Methane is an example, ethanol is an example.
Okay.
So there they already have the MDP file.
Okay.
So once we have the MDP file in each of the lambda directories,
Okay.
so now what we do, we go to the directory first. We have lambda 0, right? So we go to the directory by using the command cd.
Okay.
So now we'll in the lambda 0_00 directory we'll have the GRO file from the equilibration.
Right.
We'll have the topology file and we'll have the MDP file for free energy calculation.
Okay.
So here also the same command, we first have to generate a TPR file and then we have to do an MD run.
Okay.
So for generating a TPR file, we will use the command growmpp. So growmpp space -f space run.mdp. This is the molecular dynamics parameter file for free energy calculation. Then space -c space equal.gro, that is my equilibrated structure file. Then
Okay.
space -p, then space topol.top, which is my topology file. Then space -o space run.tpr, that is my output file. So now I will run the TPR file using the command mdrun. So mdrun, then space -v space -deff_nm space run. So the output file which is of my interest in calculating free energy is the xvg file. So we will have this run.xvg file which will contain the potential energy as a function of time. Suppose you are performing for 200 picosecond. So from 0 to 200 picosecond it will write the potential energy at each time frame. So similarly you are done calculation in lambda 00 directory. So now you will go in a lambda 01 directory. So here also you then change your init lambda value in the run.mdp
Right.
file from 0.00 to 0.1
So you have to change that in each of the directory.
in each of the directory.
Whatever actual lambda I want.
Yeah, because starting lambda point
Is
is
zero,
0, but
correct.
as you change the directory, your lambda point will also keep on changing.
Right.
So you have to change the lambda value, and then again you have to generate the TPR file, and then using the TPR file you will run mdrun, and then you will get the xvg file, that is the run.xvg file. So this is the procedure that you have to follow till lambda equal to 1.
Okay.
Right. And each lambda directory you have to change the init lambda value in the MDP file. So once you have all the xvg file in each of the lambda directory, what you do is this is the file that contain the energy differences, and this is the energy difference that we will use to calculate the free energy difference.
Correct.
So now to compute the free energy of hydration of methane, we will just type the command g_bar -b100. -b100 is it will discard the initial 100 picosecond. It will consider it as further equilibration.
Okay.
So -f lambda_star, that is it will go to all the lambda directories, and then it will take the run.xvg file from each of the lambda directories. It will calculate the free energy difference, and then it will finally display it on the screen, whatever the value of your free energy of hydration is.
So the final output delta G will be given after this command
Yeah, it will write on the screen.
on the screen.
Yeah.
It will also write in some other file, log file.
Yeah, you have to give an option for that, -o,
Okay.
and then you can also get a histogram of dh lambda as a function of lambda, how it looks.
So is that contained, where is that contained in that log file?
That is a different several output options that you will get. Once you
Okay.
type G underscore bar
Okay.
space minus H, it will give you an
Okay.
n number of options for your output file, whatever output file you want to
So
have.
suppose I want dH by d lambda at every step, there is an option to see that.
Yeah, there is an option to see that.
And you then you can also plot that dH by d lambda as a function of lambda.
Yeah, that
Huh?
that you can plot.
Okay. And sometimes that dH by d lambda, is it always having one sign or it can be different?
It can be different depending
Okay.
on your system. What is the solute?
Okay.
What is your solvent?
Okay.
Like free energy, it is different for different solute
Okay.
and solvents.
So now before running this command, should we not check whether every lambda value calculation is done properly?
Yeah, definitely that we have
Because-
to check that every lambda directory has to have this .xvg file.
Right, because even if one is missing, this will not run.
This will run, this will give you the value, but it may not give you the correct value, right? Because if one lambda point is missing,
Right. Then this will have a problem. No, it will not have that file at all.
it will give you the value of 0 at that point.
So it will
Suppose
take
it
0
will-
and do the calculation.
It will take 0 and do the calculation. So we have to make sure that all the lambda points at each lambda directory, we have the xvg file which contain the free energy differences, right?
Okay.
Suppose in lambda equal to 0 to 0.2, there is no, you haven't done calculation in lambda equal to 0.
Right.
So from 0 to 0.2, it will take some arbitrary value. It will not give you the correct value, right?
Okay.
It will start from 0.1 to 0.2, but it won't give you the value what you would expect from 0 to 0.2.
But it will not give an error saying that file missing or anything.
No, it won't give an error.
So this is, one has to be extra careful in running this then.
Yeah.
Okay.
One have to make sure that at each lambda point we have run the simulation, we have the xvg file at each lambda point. Because when you write this command G underscore bar, it will display on the screen at each lambda, like from 0 to whatever you are giving the difference from of lambda you are taking. Suppose you are from 0 to 1, you are 0.2
Okay.
you are taking, right? So 0.2, so 0 to 0.2, then 0.2 to 0.4, 0.4 to 0.6.
Okay.
It will write the value of delta G in the screen. So one can also get an idea from there
So
whether it
now
has.
the example we showed here, we were saying lambda equal to 0.01, 0.02, 0.03. It was almost linear from 0 to 1.
Yeah.
But it's not necessary like that, no, because initial values the lambda has to be very close to each other.
Yeah, because
Later values it can be very different, no?
yeah, later values you can
Because once I have switched on 80% of the potential,
Yeah,
then the differences need not be 0.01.
no,
They
no,
can
you can the differences can be small.
small or larger.
Yeah,
You may need
because
larger.
initially we have taken the difference very small because you will get a converged result.
Correct.
Otherwise, from 0 to
Suppose
0.4
it-
you take suddenly, it
Then
won't
right.
give you the correct result. You
Correct.
suddenly switch on the interaction from 0 to 0.4.
So now the way you have described here, you have to do simulations in each of the 100 directories.
Yes.
Is there a way I can give a command where it will simulate in all the directories? Can you create some file
Then
like that?
Then you'll have to have a script file for that.
Okay.
So then it will go to each lambda directory, it will perform the simulation, then it will go to other lambda, then it will perform the simulation.
Correct.
So it will take some time to do that.
So maybe we can, in our website, we can put examples of script files also, so that people
there are
can
script
use
files
that.
which you can use to run. You need not go to each and every lambda point.
Does the
In that-
manual also recommend this, or the manual doesn't say
in
about
manual,
script files?
There are like only 5 lambda points that they are showing for
Okay.
practice purpose, right? So
Okay.
they really don't show the script file.
Okay.
But while we do free energy or solvation of ethanol, they do use a script file there. They have
Okay.
given a format of the script file.
Okay.
And while you use a script file, the possibility that you miss one lambda point is also
Very
reduced.
large, correct. Suppose there is some crash in between, you will not know at all.
No, but then it will also give me an error file where I can see that what is my error, where my simulation stopped. And if
Okay.
I run through a script file, the chances that I miss one lambda directory will also be less because
Correct.
it will cover all the lambda points.
That's right, that's right, that's right. And in this case, does it write many coordinates or just writes the potential energy?
Coordinate, it depends on you whether you want to write the coordinates or not.
Because we don't really need the coordinates.
don't really need the coordinates.
Because
We
unnecessarily it will just
Yeah,
fill up
we
the
just
disk.
need the energy differences. If you don't need the coordinate, you
Okay.
just write in the MDP file that NXT out, you write it 0. It won't give you any coordinate.
Okay, okay. So when you these kind of free, you said there are two different minimization. No? One is a thermodynamic integration. There is another method for small molecules. No,
That is the test particle insertion method.
right. This is doing the thermodynamic integration.
Yeah.
Is there a easy way to do the test particle insertion? Is there an algorithm given, or is there an option in GROMACS, or that is
Yeah,
separate?
there's an option in GROMACS. Like here, while we do free energy using a thermodynamic integration method, we use this stochastic dynamics, right?
Okay.
We use as an integrator, we give their SD. So
Okay.
in test particle insertion method, you have to write TPI.
Okay.
So it will perform simulation according to the test particle insertion method.
So there also.
There we don't need different lambda points.
Okay. So, and is there some limit to the size, because
Yeah, there's a limit. You cannot go beyond like neopentane or something.
okay, only small particles
Small
can be
vol-
done,
yeah,
test
yeah.
particle integration.
Yeah.
So, can you do the free energy of very large molecules with this, or there is some limitation? Suppose I want to know the solvation free energy of a protein. Is it possible to do this?
Yeah, maybe.
Huh?
I mean,
But are
people-
there some examples in literature, or not too many?
There might be some example. I have to look
Okay.
after that.
Small peptide they must have solvated
Yeah,
easily?
yeah, small peptides they must have, because peptides, even
Right.
fullerenes they have solvated. C180 they have solvated.
Okay.
They have
So-
calculated the free energy of hydration. So I guess small peptides in C180 the size may be more or less
Okay.
similar.
So far what we have done a simple simulation of liquid argon, then we did simulation of water, then water methanol mixtures, then we considered an S peptide, and then we considered this free energy of solvation. So I think these 5 examples give you a good spectrum of different types of things that you can do with GROMACS simulations. So in our demonstration, we will demonstrate all these 5 things, and we will give you assignments to do simulations on different molecules which are similar to this. So once you do this, you will have a fairly good knowledge of what an MD simulation means and what are the kind of things you can do with the simulations. So with this, although these programs are very involved, maybe in our earlier discussion we will try to do a very simple liquid argon simulation using our own program. That also we will try to do, so that you know all the details of the algorithm of the simulation. So with this kind of a background, now you have already done simple Fortran programming for several situations like matrix multiplication, matrix inversion, Fourier transforms and so on. And with molecular dynamics programs, you have done detailed calculations which can have a real impact and also a comparison with experimental data. So this will really give you good practice on computational chemistry, and I hope you will enjoy all these calculations. And if you need any help, you have our email addresses and you can write to us, so that whatever difficulties you have, we will be able to solve it. With this lecture, we have now come to the end of our course, Computational Chemistry and Classical Molecular Dynamics. Let me summarize what we have done so far and what is expected from you. After an introduction to the methods of computer programming using a common language such as Fortran, we have studied many common numerical methods such as interpolation, curve fitting, matrix methods, finding roots of equations, integration and differential equations, and also the use of random numbers. While programming skills take a long time to develop, there are excellent public domain software such as Scilab, and we have also used Scilab software to supplement our understanding of numerical methods. While Scilab is very easy to use, it is good to have a knowledge of the programs and algorithms for at least some of the numerical methods such as matrix inversion, roots of equations and Fourier transforms. Because if we do not have basic understanding of the algorithms, just using computers should not be a technique like clicking a mouse and getting a result. So, algorithms are at the very root of programming, and you should be able to appreciate as well as use algorithms to write your own simple programs. Now, after programming in Fortran and the use of Scilab, we took up the problem of classical molecular dynamics simulations. These are now being used to understand a lot of macroscopic chemistry as well as biology.
We illustrated molecular dynamics by using a simple program on liquid argon using our own program, and then used public domain software such as GROMACS to do molecular dynamic simulations on simple liquids, liquid mixtures, ions in solution as well as peptides in water. An exposure to this course will help you to appreciate computational chemistry through first hand experience and then enable you to explore more advanced computational chemistry. Currently, the scope of computational chemistry is increasing every day. The strength of the present course is the hands-on experience in the use of numerical methods and other public domain softwares to perform chemical computation. After every lecture, you will be required to complete 1 or 2 assignments so that you get a practical and first-hand knowledge of what has been described in the lectures. If you need assistance, it will be available through TAs as well as through email. Hope you enjoy participating in this course, and we appreciate our association with you. Thank you very much and our best wishes.